Launched in August 1977, Voyager 2 embarked on its ambitious journey through the outer solar system. Its main mission was to study Jupiter, Saturn, Uranus, and Neptune. After almost 10 years, when the spacecraft briefly visited the planet Uranus in January 1986, it offered us our first ever close-up look at the mysterious ice giant. It was a monumental moment, full of discoveries that puzzled and amazed scientists. Our understanding of Uranus has been shaped almost entirely by this single spacecraft flyby. But, as it turns out, Voyager 2 might have caught Uranus on an off day, and what we learned that day was mostly misleading. While the data it provided was groundbreaking, it painted a picture of Uranus under rare and highly unusual conditions. Voyager 2 observed the planet during a period of extreme solar wind compression, which dramatically altered its magnetosphere and likely influenced many of the findings. As a result, much of what we think we know about Uranus's environment, from its magnetosphere to its radiation belts, might not represent its typical state, a cosmic coincidence that misshaped how we've understood the planet's magnetic field for nearly 4 decades. Let's have a closer look. Uranus, like Earth and other planets, has a magnetic field. This field forms a magnetosphere, a protective bubble that shields the planet from solar wind, which is the constant stream of charged particles flowing from the Sun. But during Voyager 2's flyby, Uranus's magnetosphere looked bizarre. First, the magnetic field was strangely tilted and off-center, as if someone had knocked it askew. Second, Voyager 2 detected unusually intense belts of high-energy electrons, radiation far stronger than anyone expected. And third, Uranus's magnetosphere appeared almost empty of plasma, a puzzling observation given that the planet's icy moons should be feeding particles into it. Scientists spent decades scratching their heads, theorizing that Uranus had an extreme and uniquely chaotic magnetosphere. But an analysis has uncovered an intriguing twist. Voyager 2 likely arrived during a rare and dramatic space weather event that temporarily transformed Uranus's magnetosphere. In an article published recently in Nature Astronomy, researchers at the NASA Jet Propulsion Laboratory very carefully re-examined all data from Voyager 2. In this figure, you can see the solar wind dynamic pressure data in the days preceding the Voyager 2 flyby. The dashed line indicates the start of the flyby, and you can see we are at the beginning of an exponential increase. Here's what likely happened. In the days leading up to the flyby, a powerful surge of solar wind struck Voyager 2 and Uranus. This intense stream of particles compressed the planet's magnetosphere, squashing it down to just a fraction of its usual size. When the solar wind compresses a planet's magnetosphere, it triggers a lot of activity. For example, on Earth, it causes the astonishing bright auroras and can energize radiation belts. On Uranus, something similar likely happened. On this figure, in red you can see the magnetopause subsolar standoff distance measured by Voyager 2. That is the distance between the center of the planet and the point of the protective magnetic bubble closest to the Sun. This distance is very important to understand the properties and behavior of a planet, and measuring it was one of the main goals of Voyager 2. It was measured to be just 17 RU, with 1 RU being Uranus radii, that is to say about 25,559 kilometers, and so 17 RU means 17 times the radius of the planet. But now, taking into consideration all discoveries since the 80s, scientists estimates the magnetopause distance to be more like this black line. Its average distance is about 22 RU. It might even extend to about 28 Uranus radii, but compared to what it was during Voyager 2's approach, that is a massive 23 to 40% reduction in size. This compression likely caused changes in how the magnetic field behaved and how plasma or charged particles moved around inside the magnetosphere. It's like Uranus's magnetosphere had been cleaned out right before the spacecraft arrived. Such conditions are extremely rare. Scientists have estimated that it might occur less than 5% of the time. But the timing of Voyager 2's visit meant it only captured this unusual squash state. If Voyager 2 had arrived just a few days earlier, it would have encountered a much calmer magnetosphere, vastly different from what it observed. It's like visiting a city during a rare flood and assuming that's how it always looks. This discovery teaches us an important lesson. A single snapshot can't capture the full story. To truly understand Uranus's magnetosphere, its plasma, radiation belts, and magnetic dynamics, we need more than a brief flyby. We need a dedicated mission that can observe the planet over weeks, months, or even years. Even more intriguing, if the scientist estimation of 22 RU magnetosphere is correct, that would mean that Uranus's two outermost major moons, Oberon and Titania, may be inside the magnetic bubble. These moons are located at approximately 17 and 22.8 RU from the planet, with analysis finding that they would rarely leave the magnetosphere. Titania only 4% of the time and Oberon less than 13% based on the paper. The presence of icy surface and dynamic magnetic field would make them intriguing candidates for hosting oceans beneath their icy surfaces. Of course, further experiment would need to confirm it. The planet Uranus and our universe still has many secrets waiting to be uncovered. Stay tuned if you want more.